Okay, so we looked at our polynomials last time. This time we're going to talk about some different properties of some power series. So the first thing we want to do is come up with our definition. And so again, I'm going to write out this definition because I think it has a lot of information in it, and then we want to go from there. Okay, so the first thing we have is our definition of our power series. All right, so with our definition of a power series has this general form. Of k goes from 0 to infinity of c sub k x minus a to the k. Look familiar? Yep. Okay. So now let's talk about what this means here a little bit with our definition, where a and c sub k are real numbers. And x is a variable. Okay. The c sub k's are coefficients of the power series and A is the center of the power series. Try again. Okay, the set of values of x for which the power series converges is called the interval of convergence. Interval of convergence. Man, my handwriting is terrible, you guys. Holy crapanoly. Look at this. Oh, crud. Is its interval, oh my goodness, of convergence. Oh. Okay, so the interval of convergence. Okay, so bear with me. I know this is super boring. Bear with me. We're going to get through this because there's a lot of good vocabulary in this that we're going to need to use. All right, so stick with me. We've got this. The radius of convergence of the power series denoted R is the distance from the center of the series to the boundary of the interval of convergence. Okay, here's the dealio, yo. So check this out. I'm going to get my little pointer here, and I'm going to get my pink. Let's go pink, and I'm going to make this a little bit thicker. Okie doke. So here's the power series. This we have seen before, right? So we've looked at this. We know what's going to happen. This So this is general power series. So I'm just focusing on general power series. Notice this is just flat out property of the power series. Our next section is going to focus us on Taylor. But here I'm just doing general old power series. So I'm not going to get real specific on this at this point, but I do want to just, here's a teaser for you. You are going to have a specific C sub K for Taylor when we get there, okay? Just like when we did our Taylor polynomial, we broke that out, but we broke it into that specific value in order to make those polynomials. We had that specific formula. Well, whenever we go to Taylor series, it's going to be the same C sub K, FYI. But this is just, what we are talking about is just generic power series, all right? Okay, A and C sub K, they're real numbers. So these are actual values. The only variable that I'm looking at here is going to be my x, right? Because the x is the variable. Okay, so we have coefficients and the center. Same thing that we had already talked about. Now, here's the kicker, and this is what we're going to focus on. The set of values for which the power series converges is its interval of convergence. That's important. We're going to be looking at our interval of convergence because these aren't necessarily going to converge everywhere. So I can have this power series where it has the potential to only converge at a certain place. It doesn't have to be absolute convergence. It could just be a specific interval. And then within this interval, I'm going to have this radius of convergence for this power series, and that's just like you would think any other radius would be. It's from the distance from the center to the boundary of that interval. So what we're actually doing here, let's say I have this A right here, right? So I'm centered at A because that's this is the whole point, right? I'm centered at A, where A, they're real numbers and A is my center, okay? A is the center. So from A, I have this value out here. So in order to get that value, I have this radius of convergence. So out here to this outside value, this boundary, I'm going to get this is A plus R. That's what I get to that boundary. Or over here to get to this boundary, I have that same value R, and to get to this outside boundary, I'm going to take A minus R. So that boundary that we're looking at all the way around, that is my interval of convergence. And that's what I'm talking about. All right? So for a power series, it could absolutely converge, right? It could be the whole thing. That's totally legit. It could converge from negative infinity to positive infinity. Then my radius would be infinity. Okay. But for our intents and purposes, they're not all going to do that. If they don't all do that, then we have to specify, okay, where are they converging? What is this interval that I'm looking at? Okay, now I'm going to lay down some more definition type stuff here for you in this next theorem, and then we're going to put into some practice. But I want to get these theorems all out of the way first so that we can practice it. All right, theorem 11.3. This is convergence of a power series. All right, a power series, and here it is, from 0 to infinity of C sub k x minus a to the k, centered at A, converges in one of three ways. First way that this could converge, the center converges for all x. Pardon me, I said center, I meant series. The series converges for all x. Then, this is what I literally just said, right? Then the interval of convergence is negative infinity to positive infinity, and my radius of convergence is infinity. So this is kind of like what we did in the last chapter where we did all those tests for convergence. And we either said, yes, they converge, or they do, or they diverge, right? So this is literally just convergence. So I'm just saying where these converge. I'm not saying where it diverges, because these don't diverge. We'll get there. But this could be all of it. All right, the whole series converges. Sweet. That's one scenario. Here's another scenario. Scoot this up. It can converge for just a specific amount. So there is a real number R that's greater than 0, such that, that's a greater than sign. The series converges absolutely for the absolute value of x minus a is less than r, and diverges the absolute value of x minus a is greater than r, where the radius of convergence is r. All right. So what this is saying here, if I have this interval, so I have some interval here, right? And this is centered around A. We know that we're centered around A. If these values here are less than R, meaning I'm shading to the middle. So it's less than R here. So anytime you have absolute value, just any absolute value out there, and it's less than some value, you know you're shading to those insides. Alternatively, if I have any of these values, whatever they may be, and it's greater than R, I know that I am shading to the outside. That's just how that always works, right? That's just how those happen. So my interval of convergence, and this is obviously going off to infinity, but I want this interval, just this closed interval of convergence here that I'm looking at, either converges or diverges. Now, so it converges the interval of convergence. So everything outside of that is gone. This symbol is less than. However, I'm going to do a great big however, and we're going to do some examples. I don't know if this is going to be brackets or parentheses. We have a test that we're going to have to do to determine if I have this radius of convergence in this interval of convergence, if my endpoints actually converge or not. So I have this symbol, and this is just a symbol. This is part of the formula of what it is that we're looking at, but I don't want you to get lulled into that false sense there. We are going to have to test the endpoints to see if it is bracket or parentheses, if it also converges at the endpoints or not. All right, so that is the symbol. However, heads up, right? That's coming at you. Okay, I said one of three ways, so here's our third ways. It's absolute convergence, everything. It is only a specific interval, or this is when it converges, right? The series converges only at A, in which case the radius of convergence is 0. All right, so here's the deal, guys. I am not determining, let me get this where you can see it all. I am not determining divergence here. My focus is on convergence. Now I know in this one it converges just on this interval, so if it only converges on a specific interval, it's obvious that it diverges for the rest of it. But I'm not focusing on the diverging part. I'm focusing on where the power series converges. So my focus is it converges everywhere. I'm finding my interval and my radius of convergence. My interval here and my radius of convergence. My interval doesn't exist here. It converges only at a point. So you have three choices: everywhere, specific interval, only centered at A. All right? You're not determining divergence. You're just saying, where does this converge? Everywhere, just at an interval, or only at A. All right?